How's everybody doing? I wanted to go ahead and put out a video on the buck converter circuit that I built previously, and you've probably seen the video below. If not, I'll link it. Basically, I'd made a buck converter controlled by an MSP430 to act as a MPPT control from a solar panel to a battery. So this video is going to cover the circuit that you see in front of you. This was for a class again, and so it was built kind of scratch, right? And with any buck converter circuit, I would definitely try to build a PCB. I didn't have time. Ultimately, this would have gone onto a PCB. You'll see a little bit later some of the tricks that I used to be able to not use a PCB. But ultimately, this would be much better done, much easier, and you'll blow up lots less components if you actually build this on a PCB. So let's go ahead and get into this presentation here. I'll try to keep it as quick as I can. This could drag out. This topic is so huge, and the fact that I built a synchronous converter makes it even bigger. I mean, I could make a whole series just on buck converters. If there's anything missing in the video that you want to see a video of, then let me know below. Also, like and subscribe if you want to see more. So let's get moving forward. So this is just kind of an overview of the entire thing that I built. I'm doing this just so you understand where the power is coming from, where the power is going. If you look at the top left, the power is coming in from some solar panels. We strung them up so that it was about 43.5 nominal voltage. You've got an input power measurement circuit. You have an output power measurement circuit. There's a microcontroller that controls a DC to DC converter, so that the power goes into the DC to DC converter, gets measured on the input, measured on the output, and then it charges some batteries. So this is like the entirety of the circuit in a general diagram, right? With this buck converter and with most converters, you can have input filter and an output filter. The book that I used to make this design, you can find below. It's kind of a serious book, and you got to really dig into it. But it's really great content, and if you pay attention and move through the book and do kind of as the book goes along, design as you go with the book, and use the different parts of the book to go. If you find something in the book that says to do this, look up that thing in the book that if you don't understand, and figure out exactly what that is, then move back to the part. It's a very deep, thick book. It's dry, but it's really good content, and you'll learn a lot about converters in general, SMPS in general, but also you'll be able to design a circuit. Ultimately, I went through and used Excel and some other resources to get the math right on this, but if you want to see that, then comment below. Like, subscribe. Maybe I'll make an SMPS playlist, because there really needs to be something very deep diving into SMPS altogether, because switch mode power supplies is such a huge topic. Power in general, power electronics, stuff like that, huge topic. Lots of different ways to go with that. But here's the circuit. You've got an input filter, the actual pulse or PWM part of the buck converter, which is usually called the switching part or the pulse part or PWM part. Then an output filter. This is like the general overview, right? So we've got a sensor at the input of the filter, and or sensors at the input of the filter, and sensors on the output of the filter. You got a battery, it's a capacitance, your output inductance, your input capacitance, and then you've got the switching circuit. And this part is gonna control the two switches for the synchronous converter. You're gonna need this because it has a high side switch on it, right, and a low side switch, and you want to be able to control those with dead space in between, and with all the different things that you have to do with these switches. You want to be able to control them in a very controllable manner, if you will. So using a chip like this is great. I hooked a microcontroller up to the chip, and then I've got power coming in from different various places. So this is the PWM, or the switching stage. This is the quote interesting part. The part that I used for it is an IR21834. I implore you to go into the data sheet. I'll try and post that below. So this IR21834 is it's a high side, low side gate driver, and it's got bootstrap capacitance. It can bootstrap this this high side switch up to the voltage needed to drive the thing, right? So this you've got to reference this this node here, the source of this guy, in order to drive the gate of this guy. And this allows you to do that when this node here is going up and down and actually getting very, very, very high voltages on it at certain points. So this guy allows you to do that. One of the tricks, or a few of the tricks that I found, I suppose, are putting in this this gate resistance, changing the gate resistance to work well with your circuit experimentally, putting in this diode here, a lot of those little things that you learn when you're first building these sorts of things. Also, to put a resistor on the COM port, on the ground, which allows some of any sort of floating ground to be eaten up, the voltage to be eaten up by this this resistor here. Just a few things here and there that you learn as you go through this. There's probably lots of tricks online that you can find. Just look through whatever problem you're having, look through and see if you can find how people solved that in the past. So the gate driver here, it converts the microcontroller signal to usable drive voltage for the MOSFETs, right? So you can't just hook the MSP430 directly up to these guys, because like I said, this guy floats. This line right here floats. You might have ground bounce. There's a lot of things that could just fry your microcontroller that you don't want it to be tied directly to the MOSFET. Much less, most of the time your microcontroller is not going to have enough voltage on it to drive the MOSFETs properly, right? You need a good, strong signal to drive these MOSFETs. And also this this IR21834 allows you to put dead space and stuff like that. This is very important when you're doing a synchronous power supply. You want to switch the power off and on according to the correct duty cycle, but you also want to add dead space. There's a lot of different spacings that you need to make when you make this signal output into the to turn on and off the gate drivers. So basically, you got an input on this side, which is the filter, an output on this side, which is a filter, and this is the switching stage. Of course, we got power coming in and microcontroller ground and all that you would need. So the output filter stage is what I started with, and I think the book actually starts with that, and it's a good place to start. For this, I mean, you can calculate up your equivalent resistance and your equivalent capacitance. You put these all into a bank. You get your inductance and your DC resistance for the inductor. You're going to want all these values plus the battery value or your load values going into this, and then you can put them into a calculation, which you'll find in the book, to get a transfer function. The whole idea of this output filter stage is to take this voltage that is a square wave pulse, and you're going to start dragging that to be a flat voltage. But you also want to do it with the current. So as we know, current doesn't change instantaneously over time in an inductor. So we use that inductor to flatten the current coming out of the circuit. And then capacitors don't allow voltage to change instantaneously over time. So we use the capacitors to change that voltage. And this is just kind of the order of things, right? So we've got the PWM coming in from the microcontroller, which is turning on and turning off, and you get this T off versus T on, which gives you a duty cycle, and that duty cycle will give you the ultimate voltage out, right? The voltage in the inductor without the capacitors is just going to look like a positive voltage and a full negative voltage, because the voltage can change instantaneously over time in an inductor. But then the current coming out of that inductor is going to start to flatten. Now there's different frequencies and different powers and stuff where you'll get into different modes, like discontinuous current mode and stuff like that. I'll implore you to go in and look at that, or leave a comment below, and I can go make a video just over that sort of thing. So this is kind of the output filter idea. I got this from inside of the book. I figured out my transfer function. I loaded that into MATLAB, and I built some plotting to show kind of where my corner frequency was and where the filtering frequencies and stuff like that. I wanted the corner frequency to be far enough back where the frequency coming from my microcontroller would be covered. And that's kind of the idea. You want to cover that frequency enough with filtering in order to flatten. And that's kind of the idea behind the filters. You want to take out all the frequencies. When you take out all the frequencies, you're flattening that voltage and that current. So this is the transfer function that I ultimately came up with for this circuit, and put that into these. You're more than welcome to put these values into a transfer function if you want to go back and look at the different values on all the filters to get this graph and see if you're coming up with the same thing that I am. So this filter, like I said, the frequency you just want to move that over, and you want it to be a certain amount down, basically 3 dB down in the area that you're trying to drive it frequency wise. There's a lot of cool tricks. When I went and did the math, there's a lot of cool tricks that I kind of figured out that I might be able to do, like moving the frequency to stay out of discontinuous mode instead of some of the other techniques that are used. But ultimately, that's not usually a done thing. I'd like to check it out one of these days, but maybe I will, and if I do, I'll make a video over it for you guys. So this is the input filter stage for the buck converter. It's very important to get a good ceramic, very fast, low resistance capacitance built up, and then once you get that right amount of capacitance, then you add a bulk capacitance. I tried this with the ceramic capacitance and then just put a little bit of bulk on there to see, is my ceramic capacitance working? And I blew the tops right off the caps for the bulk capacitance. The reason you kind of do this, yeah, it'd be great to use ceramic capacitance for all the capacitance, but ceramic capacitance, when you're talking about lots and lots of capacitance, can cost a lot more than just buying a bulk, electrolytic, right? So you get just enough ceramic capacitance or quick capacitance to be able to handle the circuit. Then you build up your bulk capacitance, and it'll keep that bulk capacitance from hitting, very, very high peaks and troughs where it'll destroy the capacitor, right? Here's the formula down here that I use to calculate the kind of capacitance that I would need for the ceramic capacitance. Then I just kept adding lots and lots of bulk capacitance to get to the point where it was flattened enough. There's also a formula that I use to get just enough to make sure that I had enough bulk capacitance. If you blow a few tops on these things, that's the way it is. I just want to give you a warning that the tops can come off of these things, so keep your eyes away from it. I don't take any responsibility for anybody messing up their circuits or blowing, hitting an eye with a capacitor. So the big idea here is get enough ceramic capacitance to get some good smoothing, and then lots of bulk capacitance to finish it out. Now, as far as my circuit, the power measurement side of it, I used an ACS 712 current sensor. Looking back on this, I would have just gone with a shunt resistor, something like a shunt bar. You can find really, really low value resistors on like Amazon. I'll try to put one down in the description below. But they basically look like just a bar of metal, but they have a certain resistance to them. But the bar resistors, the big shunt resistors work great for measuring the current. And I'd originally gone with this ACS because I was trying to cut down power losses. Because I was looking through Mauser trying to find a good part that was a good resistor that could do all the power that I needed it to do, but also had a low enough resistance so it wasn't eating too much power. And I wound up going through and finding this Hall effect sensor, and I thought that'd be great for the project. And it turns out that I would have gone back and changed that to a different sensor ultimately, or to just a massive shunt resistor. That would work much better for this current measurement on this circuit. Now going from that, if you just have a resistor, a shunt resistor, you measure across the shunt resistor and feed that to op-amp measuring circuit or a good circuit measurement chip. The same thing I kind of did with the voltage here. On the output, I've got just basically divided the voltage down with good SMIC resistors, something that has 0.1 or better precision on it, and just divided that down, feed it to in this case, I fed it directly to the microcontroller. Now, I was a student when I did this, and I wound up frying my microcontroller. I would suggest running this to a good measurement circuit device. There's good implementation amplifiers and differential amplifiers and stuff like that. Do a little bit of research on Google. You'll find some really good circuits for working with that. There's a little bit of capacitance on here just to filter down that signal to keep it from jittering so much. So now we move into the power circuit. This is what I use to power the whole circuit, the whole MPPT Buck converter circuit. Like I said, the ultimate idea behind this and what we were pushed to do was to get as low or as high of efficiency as possible. So you see I used two different Buck converters here, or I used two different SMPS here, the EC8AW-48S15 and the 7805 SRC. These are just two different Buck converters to drive the different parts of the circuit. If you look up here, there's a microcontroller fed into an op amp that basically just turns on and off this EC8AW-48S15. So from the as far as PWM is concerned, from the microcontroller, I'm not going to go deep dive into this. You could do probably another video or a couple videos on the actual driving of the microcontroller, or driving of the DC to DC power conversion circuit. Not only that, there's a whole MPPT side of this where you do, there's perturb and disturb and all these other different things that you can do as far as solar panels are concerned and all that sort of thing. I'm just going to kind of give a quick overview here. The microcontroller basically drives the DC to DC converter as we've seen before, and all I'm doing is I've got an actual count going up, and I take that count as it's going up, and I chop off depending on where I want the duty cycle to be. So you're climbing the hill up to 512 is the whole period. We've got 384 is kind of like a counter, right? So we get up to 384 and we turn it off there, right? So that's our duty cycle control variable. Where do we want that variable? We want it at 384 out of 512. Do we want it at 10 out of 512? Do we want it at 512 out of 512? I don't think you'll ever want the 512 out of 512. If you wanted it 0 out of 512, then you basically just turn the thing off, right? So I'm just controlling this duty cycle control variable via the input signals from the current measurement and from the voltage measurement, right? And there's a good, you build up a good formula to get, what do I want out from what I've got coming in, and that actual formula down here is V in, or for V out is the duty cycle times V in. It's pretty simplistic, really. I mean, you could just do, if you just wanted a PWM signal of this thing, you could take out all the filtering and you just do, duty cycle times V in, and you'll get that PWM signal voltage over time average will be, the V out. Now, there's a lot of different things in your circuit that can eat some of the power, eat some of the voltage, eat some of the current, that might make you change this duty cycle a little bit, but this is kind of a basic, the basic general idea. Your duty cycle times your V in equals your V out. Now, once you get this kind of built up, that'll give you a good starting place. Then you go ahead and change that duty cycle a little bit to get to the voltage that you need it to be. Continue your experimentation and what you need to do to get to what you're trying to do with this. In our case, it was to drive a battery. We wanted a certain voltage for say charging, or a certain voltage for starting the charge. There's different batteries. You have different charging cycles and different stuff. So that duty cycle, or that what we wanted for V out, would change depending on what stage or what mode we were in for the MPPT. But if you just have a single output voltage that you want, you just kind of want to hit that voltage and stick at it. Now, you wouldn't even technically need a measurement there if your input voltage is constant, right? If your input voltage is constant and your output voltage is constant, you could pretty well make this circuit with just a duty cycle. But now, that being said, very, very rarely are your input and output voltages constant. In our case, we had a solar array, so that that changed all the time, and we of course wanted to change the max power point, so we were changing voltage for current to get to that proper point. But also, I mean, even coming out of the wall, if you come out of the wall, go through, a rectifier circuit, a rectifier power supply circuit, and you're going into this DC to DC converter, that voltage coming out of the wall isn't always a constant sine wave at a constant voltage. It changes in amplitude, it changes in frequency. So you can either take your lumps or you can measure it, right? And most of the time you're just going to go through and measure it. And there's actual chips out there that do almost the whole thing. They'll do the measurement, they'll do the duty cycle, they'll do all the the feedback and everything else, and you just kind of feed it, filtering and stuff. But where's the fun in that, right? So this is just kind of the idea from the microcontroller. If y'all want the code for that, maybe I could do a different video. If y'all want to dive deeper into MPPT, maybe we can do that. So I've kind of just, in the end here, before I show you kind of the results, I've included the entire circuit diagram. Feel free to take a screenshot of this and dig into it if you want. A lot of these parts and part numbers will be down below, so you can order them if you want. But basically, just kind of go quick through this. You got your input filter, then it goes down into your switching, right? And that switching is driven by your gate driver, your high-low gate driver, and that goes to an output, which is your output filter. Then off the output filter, we're measuring the current and the voltage at this point. And we actually were measuring the current and the voltage up here, basic same ways. And then your power for the whole circuit comes from these power devices down here. Basically, every single part of this has a value. If you're building this exact same circuit, sure, go for these values. Otherwise, you're going to go through and change these values. Like I said, I'll post that book down below. It's a tough read, but man, it is just a fantastic way to go through and learn all this and know it, right? And know a good portion of it. But you really got to deep dive into it and figure out all the different parts and where you're going with it. So a lot of these values that are going to change are going to be like your input filtering, your output filtering. Depending on your input voltage, you might wind up changing some of these values in here. Depending on how your circuit works, you might change some of these values in here. These parts might change. You might not need 5 volts. You might not need the voltages coming out of these guys. But this is kind of the basic layout. This chip's a great chip to work with. Make sure that it works for the specs of what you're trying to design. That's part of being an engineer, right? Like, you got to go through and you got to spec parts, you got to spec equipment, you got to spec all the things that you need. A lot of these things you can get away with cheaply, but the cheaper you go, the more you work. Of course, the more you work, the more you learn too, right? So there's kind of a good balance going on there. So here's the whole design of the circuit. You can take a screenshot and go through that if you want. So ultimately, ultimately the circuit was designed onto perf board, right? And I just kind of stuck these things through and soldered the bottom of it. Now, I'll add a video to this of the actual bottoms of these boards. It's insane on some of these boards how much solder is used. These traces have to be super, super, super thick between components on some of these parts. All this is, you've got to reduce noise, you got to reduce distances, inductance, all these parasitics on different parts of these circuits. So part of the way to make this work is to separate the noisy components, compact the whole switching circuit, use very, very thick traces, and twist your long leads. If you'll notice, this input filter, I've got these leads twisted here. This guy here has huge thick traces. This guy has huge thick traces below it. All these different circuits, especially on this side, on the hard switching side, everything has to be compact, which is why these are kind of laying over a little bit. Ultimately, like I said, this design would be great on a PCB. We just didn't have time. If I were to keep going with this would have just been a prototype and gone to a PCB. Ultimately, you would lose the starter board here, right? Like, you don't need an MSP 430 launch pad in there, right? You can pull that chip off and throw it on the board. That's not a problem either. That actually might be a cool video to do. How to design for MSP 430, direct on board. Although I'm sure there's got to be a lot of videos out there, but maybe you'll like my take on it. So let's kind of go over this real quick. This is the measurement area where you've got those current measurement sensors here, and then you've got voltage measurement going over there. You've got your output filter, your input filter, switching, And then of course your step down, this is the power board side, right? So if we were to go from that front or left to right, from the front of the circuit to the back, you would have your input filters going into switching, and then all that goes into the output filter here, and then that ultimately goes uh, to the battery, right? So you got input and output for the battery and for the solar panels. So these are the waveforms that I ultimately got out of this circuit. When you go to measure these things, I did this on my Rigol. It was fast enough. I actually really like that Rigol. I've used it a lot for a lot of different things. It takes pretty pictures. It gives me good signals. And apparently it's very hackable, which is kind of cool. Anyways, so when you go to measure these things, you've got to be really close, right up close with your measurement instrument. So if you're using probes, they've got those spring lead probes, where you can slide that spring over the sheath, and I'll make a video of that here in a second. You get that really close to the, if you're trying to measure drain to source or gate to source, if you're measuring gate to source, you want that thing right up on there. You don't want any noise in the system. I'd also add, a magnet with a few loops to do that measurement to cut down on any sort of common mode noise, some of the other stuff. So this is the measurement from the gate, and this is drain to source, right? And so you can kind of see the switching as it goes. One of the issues that I was having was a lot of ringing. Some of that ringing was due to my measurement. Some of that ringing was due to the high stray inductance and capacitance in the circuit. Some of that ringing was just due to poor design. And that's why I say all these things that I listed on this previous page are so super important. You'll blow up components, you'll get lots of ringing, you'll get a lot of problems if you don't use these techniques down here to design the circuit. So that was the high side gate and VDS. This is the low side gate and VDS. There's still some ringing there, but it's nominal. It's to a point where it's acceptable, right? And this is kind of the circuit, the output, right? So this is V in coming from the solar panels, and then V out going to a light bulb. Actually, I think is what I've measured this at, which you'll actually see in the other video that I'll link below. That's been on there for a little while. So that was the whole circuit. Here's some references to some of the material. I will also link a lot of this stuff down below. But of course, a lot of these things, they're data sheets, and it's going to depend on what you exactly use. Some of it's very important to actually use the data sheet for what part you're using. Some of this is like books and stuff. I'll link some of those down below. Some that were very very helpful, and some of the articles and stuff that I use. So.
Excuse my lab. I've got work stuff going on. Of course, with the environment now, I've had to move all my work FPGA stuff and everything else to my personal lab so we can work from home. But I'll try and get you guys a good picture of these different parts of these circuits. So let me go ahead and pull these out here. So, see if we can get this to focus. As you can see, this is the switching board with the MOSFETs on it, and I'm serious. There's tons and tons and tons of solder on there. Just built it up a lot, and actually used some different wires and stuff. Copper traces, copper wires to go between each piece, and then just built up that solder as much as I could. You got to be real close or real careful about doing solder bridges between some of those connections, but you really got to build it up. And you'll see on the filter circuit as well, I think the output filter, I just used tons and tons of solder. This is to cut down on the stray inductance. Really, the big gig here is stray inductance. You don't want too much stray inductance in it. So that's part of the gig. You also notice everything here is very close together, or at least as close together as possible. You got the driver chip down in there. I've got a bunch of all the different parts are just like built right in as close as I could get them. Of course, there's some heat sinks on the MOSFETs, but yeah, getting everything as close as possible. If you'll notice down inside of, between these two capacitors here, that's kind of a bulk capacitance area. Between those, I've got a bunch of ceramic capacitors just kind of built in, and I'm getting them as close as I can. You know, I put them underneath a perf board between two perf boards to get them as close as I can to each other and to the actual circuit, to build up that bulk capacitance, cut down on inductance and stuff like that. So that's what you really want to go for when you're building a circuit like this. Everything's got to be super thick traces. I mean, if you can see how deep some of these traces are, they're standing off the board quite a bit. Um, you got to get super thick traces, cut out as much stray inductance as you can, and from there it should work. Most of the problems that I've had with any of this is the stray inductance. It's just stray inductance, stray capacitance. A little bit of an issue, but really, really big on the stray inductance.
All right. Thank you guys for sticking around. Don't forget to love well.